Hey guys, it's Dr. D-Flo, and in today's video we'll be taking waste plastic, grinding it up, and re-extruding it as recycled 3D printer filament to give it a second life. This is part 2 of my extrusion series, so be sure to check out the first video, which showcases the technology and materials that go into producing filament. The goal of this video is to provide you with a realistic look at the mechanical recycling of plastics, a process that's more challenging than you might expect. Many of the economical and logistical issues of recycling comes from sourcing clean and meticulously sorted plastics. In this makerspace, I have resin-specific bins so students can self-sort their unwanted 3D prints by filament type. We will start this video by recycling these items, but we'll circle back and attempt to turn common household items like these PET water bottles into filament. And with that, let's get started.
Dr. D-Flo.
All the recycling equipment that we'll be using today has been provided by Filament. These machines are the most powerful tools that you can purchase that can still run off residential power. I mean, look at the size of this motor. It's hard to believe that a 110-volt outlet is sufficient, but it is. We will discuss the economics of purchasing this equipment later on because frankly, these items would be quite expensive for the hobbyist. But they do work well, as I've been using this recycling lineup for a little over a year and I've made filament from close to 100 kilograms of recycled material. So let's get into the process. As discussed in the first video, input for the filament extruder is pelleted material of approximately 3 to 4 millimeters in diameter. This material fits between the flights of the screw, which ultimately conveys it forward and melts it. Of course, our bin full of unwanted PLA parts are too large to fit within the flights of the screw. So how do we break these large parts down into tiny pieces? Well, if you're thinking of using a hammer or a saw, then you wouldn't be too far off. But in our case, this shredding process is handled by this machine known as the reclaimer. Large parts go into the top of the hopper and small chunks come out. It's that simple. But garbage in equals garbage out. Only components that are not painted or glued and are free from screws, heat set inserts, and other material not made from the base plastic can be recycled. If the plastic is dirty, then it must be washed. It's important to realize that anything going into the reclaimer will be in the final spool of filament. This includes the color of the recycled material. Shredding parts of different colors will result in a filament that trends to a brownish or black color. It's not possible to recolor this material to something lighter. For this reason, I try to also sort my plastics based on color. For this walkthrough, we're going to be using these red trinkets. Let's take a closer look at how the reclaimer works. If I pop open one of the hoppers, then you can see the blades that cut and crush the material as they rotate, leaving behind shredded material. The reclaimer has 2 different sets of blades, both with independent hoppers. The set on the right, known as the shredder, has very large teeth to grab the part and smash it against the walls of the chamber, fracturing the plastic. On the second pass, any pieces that are small enough will follow the blades through the openings that they rotate through and exit out the bottom into a bin. Larger pieces will be crushed again. This will repeat over and over again until there's nothing left in the chamber. Take a listen to the shredder and get a feel for its throughput. It took about 30 minutes for the reclaimer to shred about 1 kilogram of plastic parts. Now, the ability of the shredder to grab a hold of the plastic depends largely on the size of the blades. While larger blades are able to shred larger material, there are also wider openings in the base for the blades to rotate through and the plastic to follow. For this reason, the size of the plastic fragments leaving the shredder on the right is too large for the extruder. Most of these pieces are about 8 to 12 millimeters in diameter. We need about half this size. To produce a finer output, the material must go through a secondary shredder with smaller blades. You can see the blades on the left side are about half the thickness compared to those on the right. Filament calls this set of thinner blades the granulator. We can pour our previously shredded material into the granulator. Take a listen to the granulator in action. The more uniform material going into the granulator allows it to process it quicker, so it took about 15 minutes to take that kilogram of shredded material and granulate it. A quick measurement shows that the granulated material, or what I refer to as regrind, is ready to be extruded as filament. But before we go to the next step, let's talk about the most glaring limitation of using a desktop shredder, the maximum part size. You can see on this label that a 3-inch diameter sphere is the largest part that can be placed in the hopper, which is smaller than a fist. This size restriction is likely because larger parts will require larger and more numerous blades to shred, which in turn will require more power to turn. Filament has constrained themselves to a 110 volt, 10 amp outlet, so a 1 horsepower motor is about as large as you can go without tripping a breaker. However, Filament did try to squeeze out as much torque as possible with this power limitation. With some of the covers removed, you can see that the motor shaft drives a 20-to-1 worm gearbox, with the output of that rotating a 2.5-to-1 roller chain, which ultimately turns the shaft that the blades are attached to. This is plenty of torque for parts under 3-inch diameter, and I've never had the reclaimer stall. However, you do have to ask yourself, how many parts am I printing that are this size? Of course, a reciprocating saw can get any 3D printed object down to 3-inch pieces, but this can be a lot of work, especially if you're printing thin wall parts such as these trays and enclosures. Perhaps purchasing a larger shredder with the output feeding into the reclaimer would be a good solution for those who need to recycle parts that take up most of a print bed. I will explore this further when we talk about the economics of recycling plastic. One more issue that I want to discuss with the reclaimer is that even when the parts are smaller than that 3-inch diameter, their shape can affect the ability of the shredder's blades to grab a hold. Intricate geometries are the easiest to shred, as there's usually ledges and surface texture that allow the blades to suck the material in. Round and flat objects are more likely to bounce around inside the chamber. When you run the reclaimer for a while, you can spot the parts that will shred well and those that won't. These limitations of size and shape make it almost impossible to grind up common household recyclables, such as cleaning containers and water bottles. We will discuss how I attempt to recycle these later, but I don't want to leave the reclaimer on a bad note. Given the correct size, this machine can quickly revert old prints back into granules that can be re-extruded, which we will tackle now. The shredding significantly increased the surface area of the plastic, making it easier for it to absorb water. As discussed in part 1, water content in the pellets can cause voids and bubbles in the filament. But what I didn't mention was that many plastics can degrade when heated above their melting temperatures in the presence of water. This is known as hydrolysis and will cause parts that are printed from the degraded filament to be brittle and weak. PLA is particularly susceptible to hydrolytic degradation, and being aware of the plastic's tendency to degrade at high temperatures will be an important theme for these later steps. I dried the regrind in an oven to remove as much moisture as possible. So we have dry PLA regrind. This should extrude exactly the same as the pellets, right? Well, unfortunately not, or else this video would be much shorter. If you've ever handled ground up plastic, then you know right away it's much lighter than pellets given the same volume. But to show this visually, I can melt both pellets and regrind to compare. Here you can see that when 25 cubic centimeters or 25 milliliters of pellets are melted, they take up about 15 milliliters. The regrind, on the other hand, doesn't yield as clean of a result, but estimating for the material on the wall and the void in the middle, there is likely 8 to 9 milliliters of melt. So this means that our regrind weighs less for the same volume of material, and the technical word for this is bulk density. The regrind has a lower bulk density than the pellets. Now I could have just weighed the material to calculate bulk density, which I did. Regrind weighs half as much as the pellets, but through this melting demonstration, I'm able to show a difference in this melting behavior. Both the pellets and regrind were heated in the same oven for the same duration. The new pellets flowed to the bottom of the cylinder as they melted, but the regrind flowed less consistently, forming clumps near the wall. The major difference between these two materials besides the red colorant is that the recycled material has gone through 2 additional heating cycles when first extruded as a filament and then 3D printed into an object. This comes back to our theme that plastics have a tendency to degrade at high temperatures. The more times the plastic is processed, the less it will be like the new material. Keeping track of the number of times a plastic is heated is known as its thermal history. Some plastics can withstand a long thermal history, such as PET and polystyrene, without a significant change in mechanical properties. These plastics are considered highly recyclable. I'm starting off with PLA because this plastic is synonymous with 3D printing, but PLA is not very recyclable because of its tendency to degrade. In fact, it's often marketed as a biodegradable plastic. With this in mind, industrial extruders that process recycled PLA or other plastics combine old material with new pellets to prevent severe loss of mechanical properties in the final product. However, the mixture of regrind and pellets is highly variable in size, which can result in an unstable output from the extruder. This problem is best explained visually. Let's pretend that I can unwrap this screw that conveys and melts the plastic in the extruder. This rectangle represents the space that can be occupied by the plastic granules in a single flight of the screw. This rectangle can be completely filled with pellets, regrind, or some combination of the two. We know the most amount of material will be conveyed through the extruder if the rectangle is filled with just pellets. The least amount of material if it just contains regrind, because the regrind has a lower bulk density. Ideally, when you mix regrind and pellets together, each flight would have the same ratio. But it is difficult to blend these two forms of PLA together due to the irregular shape and size distribution of the regrind. Therefore, the ratio of regrind to pellets can change for each flight of the screw, meaning that each flight contains a different mass of material. As the screw rotates, it is pushing a variable amount of plastic out of the extruder's die. This results in random under and over extrusion of the filament. To demonstrate this problem, I created two different ratios of regrind to pellets. First, I have 25 weight percent regrind, with the other 75% of the mass being pellets. I was able to spool the filament, but I needed to constantly adjust the drive wheel speed. I had a small amount of success in the beginning with keeping the filament diameter within the plus minus 50 micron lines, but eventually the output was so variable I could not change the speed fast enough. As you might expect, increasing the amount of regrind to 50 weight percent increased the problems. I was not able to spool the filament because the output was swinging from 1 to 2 millimeters, but even more troublesome, the material was overheating and losing its shape due to a loss of its viscosity. If the filament is too soft, then it can't be pulled towards the spooler. Instead, it will pile up right next to the die. The combination of the motor consuming a lot of amps and there being a low output resulted in a small amount of material being exposed to significant viscous heating. Overheating will always be a concern when processing regrind. So clearly, this setup cannot extrude regrind and pellets simultaneously. This is possible, however, with purpose-built screw extruders that use a special barrel to compress the regrind for more uniform solid conveyance. But it's not possible to switch barrels on the X6, so what's the solution? Well, this is the part I was talking about in the intro when I said that recycling failed prints is more difficult than you may expect. To get the regrind to have the same bulk density and shape as the pellets, I'm going to have to extrude a 3mm diameter filament of 100% regrind, pelletize it back into 3mm pellets, then mix the recycled pellets with virgin pellets, and then extrude again to make the final filament. I'm going to bring you through all the steps. Let's start by swapping out the 1.75mm die on the extruder for a 3mm one. Before I pour the regrind into the extruder, I'm going to use this sieve to remove any plastic powder from the bulk material that has been over-granulated. Known as fines in the industry, small particles are strangely very difficult to process. They are difficult to melt, entrap air, and don't mix well with other materials. In plastic extrusion, there's a sweet spot between particles that are too large and those that are too small. That diameter range for suitable materials is 1 to 5 millimeters for this extruder. With the hopper loaded up, I can extrude this material like it's PLA, but I need to go at a slower speed to minimize overheating. I'm going to spool it temporarily just to store it before pelletizing. There are several drawbacks to this process. Not only does it double the time to make a spool of filament, but it also adds to the thermal history of the material. Fortunately, mixing in fresh PLA should help with this. The tolerance for this temporary 3mm filament is much more relaxed. The upper limit is 3.5 millimeters because that's the largest size the pelletizer will accept. The lower limit would be around 2 millimeters. The more uniform we can get the size, the more consistent output during re-extrusion, but we're running 100% regrind, so fluctuations are expected. To turn this 100% recycled spool into pellets for a second round of extrusion, we get to use the pelletizer. This no-frills machine has a 1/2 horsepower motor that spins a 6-flute, 1-inch high-speed steel cutter that slices through the filament. Filament has elected to use a standard end mill for the cutter, so it is very easy to replace when it gets dull, and the off-the-shelf part is not too expensive. With the pelletizer on, you can see the cutter rotating. The size of the pellets will depend on two factors: the rotational speed of the cutter, which can be adjusted by this knob here, and the rate at which the filament is fed in. A slow RPM of the cutter and a fast feed rate will cause the pellets to be longer, with the opposite resulting in shorter pellets. Again, we want our recycled pellets to be as close to the virgin pellets for uniform mixing and conveying in the screw extruder, so a length of about 3 millimeters is ideal. With some practice, you can feed the filament into the pelletizer by hand, which is a very quick way to use up the remaining filament on an almost empty spool, or to recover the material that piles up on the side when you're adjusting the drive speed prior to spooling. I produce several kilograms a month just from pelletizing those scraps. But because these pellets have about half the diameter of a standard pellet, when I process this material, I don't mix in virgin pellets. This is the only time I extrude 100% recycled material. Of course, this didn't go through the first printing cycle, so it has a lower thermal history. Feeding the material by hand can be tedious and prone to variability. So to automate the process, the pelletizer ships with this attachment that connects to the spooler just behind the drive wheels. The wedge shape of this piece funnels the filament to this tube, which will of course constrain the path of the filament to the pelletizer. This allows me to control the feed rate of the filament with the drive wheel speed. Turn the cutter back on, turn the drive on, now it's just a matter of fine-tuning both the drive speed and the cutter speed to get the desired pellet size. The rest is automatic. Now that we have our bin of recycled pellets, let's talk about what percentage of new pellets should be added back into our final feedstock for the extruder. Researchers who have studied the recyclability of PLA have shown that this material gradually loses its mechanical properties with each time it's recycled, due to its thermal history, as well as other factors related to mechanically grinding up the plastic. For the first 100% recycled spool, it would be difficult to discern a change in quality, especially as most PLA parts are normally used for artistic models rather than for structural purposes. However, with each subsequent time through the screw extruder and 3D printer extruder, the mechanical properties drop quickly. This loss in mechanical properties is often due to a decrease in the molecular weight of the plastic. Plastics, or polymers, are composed of long chains that consist of repeating monomers. The longer these chains, the higher the polymer's molecular weight. Chain length and molecular weight correlates with the bulk material strength, toughness, and heat resistance, all properties you would like to see in a final 3D printed part. But plastic degradation can cause the polymer chains to be broken down into smaller fragments, taking these properties away. Further, chain length also drives viscosity. When heated, longer chains require more convincing to flow and induce a higher viscosity in the plastic. When 3D printing, a high melt viscosity is beneficial because it allows for a precise control over the flow and position of the material as it comes out of the nozzle. A low melt viscosity can cause sagging of the print layers, oozing of the nozzle, and dimensional growth of the print. These studies of PLA's recyclability are also performed in a controlled environment. The parts in my PLA recycling bin may have been exposed to photodegradation from the sunlight and chemical degradation from cleaning products, which further decrease their recyclability. Also, I have to rely on students to only put PLA parts in the PLA bin. The accidental inclusion of foreign plastics in the recycling process can destroy the mechanical properties of the base material. It's really not economical to confirm the identity of each plastic with spectroscopy or a solvent-based sorting technique. So for all these reasons, I use at most 50% recycled pellets when producing filament. However, due to how time-consuming the recycling process is, and my makerspace's high consumption of filament, I use closer to 25% reused pellets simply because I cannot produce enough recycled material. But for this example spool, I'm going to use a 50-50 blend. For the fresh pellets, I need to add half of the normal amount of colorant because the recycled pellets are already colored red. Mix these together, shake them up, and then put them in the hopper. With our 2 spools finished, let's dive into the economics of recycling unwanted 3D prints back into filament. There are 2 reasons to recycle parts. The first is to cut down on waste going to landfills, and the second is to save money. While a bit pessimistic, I think most of us can agree that the opportunity to produce cheaper filament is the primary driver for why you would purchase a setup like this. However, the amount of money that you will save is directly tied to the price of new pellets. The more expensive the new material is, the more likely you'd be to recapture the value of an unwanted part through recycling. Unfortunately, plastic pellets have been and remain a very cheap commodity. As discussed in the last video, PLA is about $6 per kilogram when purchased in bulk, with most other plastics having a similar cost. At the time of recording, Filament sells the reclaimer and the pelletizer as a pair for $12,000, which means that you will have to recycle about 2,000 kilograms of waste PLA or similar to realize a return on your investment. While it is possible to recycle 2 metric tons with this equipment, it will be very time consuming, as you've probably already gotten a sense for. But let's go ahead and total up the time for recycling 1 kilogram of material. The first shredding pass with the reclaimer was 30 minutes, and the second pass through the granulating section was an additional 15 minutes. Extruding the regrind was 1 hour for a kilogram spool. I had to extrude slower to prevent overheating of the irregular material. Pelletizing the 3mm filament was about 15 minutes, and finally re-extruding the product was another 30 minutes. This totals to 2.5 hours for processing 1 kilogram of recycled material. Extrapolating, it would take 625 8-hour workdays to go through all 2,000 kilograms. Most of the Filament machines can be run without intervention, but you do have to reload the hoppers, swap spools, and collect the output from the pelletizer. My point here is that you are unlikely to make money with this recycling setup, especially with labor included. So why would you purchase equipment like this? Well, in my case, these tools are the perfect scale for teaching how plastic is mechanically recycled. Industrial equipment operates nearly identical, just at a much larger and of course more efficient scale. Also, this is just my opinion, but I do believe that the cost of plastics will continue to rise. Not because they are getting more expensive to produce, but it's likely that governments will tax the production of new resins to encourage the recycling of old ones. If the price of new pellets were about 5 times as expensive as today's prices, then recycling at home or in a makerspace or small business could be very economical. But let's say that you are motivated to recycle waste plastic for environmental reasons versus for profit. Well, tapping into the vast waste stream of commodity plastics that are produced by households would be a great way to start. Let's jump into the next section on converting waste PET drink bottles and containers into 3D printer filament. To quote the Barbie song, life in plastic, it's fantastic. But really, the plastic revolution, which began in the mid-20th century, has enabled the comforts of modern society. Plastics have increased the shelf life of food, offered a lightweight and corrosion-resistant alternative to construction components, and allowed for single-use packaging, whether that is for sterile medical instruments or utensils for your to-go meal. It is impossible to imagine a world without plastics, which is one of the reasons why it is so difficult to convince people to cut back on their use. But it is clear that the nearly 300 million metric tons of plastic waste produced last year alone poses significant environmental and sustainability challenges. I'm not saying that turning plastic bottles and containers into 3D printer filament is the solution to this problem, but finding creative ways to reuse waste plastic is a small part, of a multifaceted approach to dealing with this problem. Let's dive into the process by first identifying what plastic waste can be turned into filament. Most containers are labeled with a resin identification code, which is a number inside a triangle of arrows. Take a look at this chart, which matches the identification code with the base plastic. Most consumer items are made from number 1, polyethylene terephthalate, or PET, which includes water and soda bottles. Number 2, high-density polyethylene, or HDPE, which is often found in cleaning containers. Number 4, low-density polyethylene, or LDPE, which is used for plastic bags and wrap. And finally, number 5, polypropylene, used for food containers. I mentioned both polyethylene and polypropylene in my previous filament extrusion video in the context that these materials have a high crystallinity, which makes them difficult to 3D print due to extreme warping. So we will have to avoid containers with number 2, number 4, and number 5 recycling numbers. That leaves us with PET. If you've been 3D printing for a while, then you may be familiar with PETG. The difference between PET and PETG is a glycol modification. The glycol disrupts the regularity of the polymer chain in PETG, reducing its overall crystallinity. This means that it's easier to print PETG, but that doesn't mean PET is unprintable, especially under the right conditions. While PET and PETG have similar molecular structures, they cannot be recycled together because of different processing temperatures. Several years ago, a law passed in California disqualified PETG containers from using the number 1 recycling designator. This is a bigger deal than you might think, as there are tax incentives for manufacturing containers from recyclable plastics. So this law made it largely uneconomical to make single-use parts from PETG. So to quickly summarize, PET waste plastic is the best material to recycle into 3D printer filament due to its availability and 3D printability. However, it won't print as well as its brother PETG and should not be mixed with it either. PET bottles will be the start of our recycling stream for this section. We're going to use my Filament equipment to recycle these bottles, but you may be familiar with YouTube videos that make it seem as if you are one bottle peeler and extruder away from having an endless amount of PET filament. Of course, I was curious how the output of one of these bottle extruders would compare to my recycling lineup, especially since it is a fraction of the cost. I was hoping that I could feed the filament from this contraption into my pelletizer. With this bottle peeler and extruder, I was trying to circumvent the inability of the reclaimer to efficiently grind down the plastic bottles. Even when the bottle is crushed, the shredder's teeth are not the correct geometry and size to efficiently rip the flexible plastic apart. Also, the output of shredding thin film containers is a very difficult to process flake, which will be discussed later in this section. Unfortunately, there were several issues with the bottle re-extruder, but perhaps the most important is the low throughput, which in my hands was close to an hour per bottle. And when a 2-liter bottle only contains 50 grams of plastic, it will take 20 hours to make a single spool of filament. This time estimate doesn't include having to remove all the creases out of the bottle by inflating with a tire pump and then using a hot air gun on it before it can be pulled into a strip. Also, the resultant filament is more of a round tube than a solid fiber, which will cause under-extrusion if used directly on a filament 3D printer. I don't want to be too negative about the bottle peeler setup because it is a great learning tool and it's exciting to print that first part out of 100% recycled material, but it's simply not the right tool for recycling any more than a handful of bottles. So to generate enough regrind to feed the extruder, I turned to my friends over at the Action Box YouTube channel who offer a DIY plastic shredder. Unlike other low-cost shredders, which are underpowered, Shreddy is a 2-horsepower beast that makes quick work of plastic bottles. Take a look at the new 5.0 version sucking a bottle in and spitting it out after only a couple of seconds. Compared to my reclaimer, Shreddy not only has more blades, but each blade has larger and more aggressive teeth, which have no problem grabbing a hold of the thin wall plastic bottles. Dave and Alan's design includes 2 different sets of teeth, which are rotating by independent motors. Varying the RPM of each set of blades together or separately allows for different shearing or cutting profiles to be achieved. Higher shear is ideal for tougher materials, and lower shear for materials that tend to be over-granulated. Before putting a water bottle into Shreddy, the bottle cap and seal must be removed because these are typically either polyethylene or polypropylene and not PET. We don't want to mix plastics as this will degrade the mechanical properties of the final product as discussed before. Also, it's important to remove the outside labeling as this is a different plastic too. For containers used to hold anything but water, they will need a quick rinse to remove any lasting residues. The shredded material that comes out of Shreddy is not able to go right into the X6 extruder. It's too large. But fortunately, it is the right size for the granulator side of the reclaimer. After granulating the material a final time, we have a material that is small enough to fit between the flights of the X6 screw. But there is one more problem. The irregular shape of regrind can cause more than just a low bulk density. It can also affect the ability of the solids to follow gravity down the hopper and into the rotating flights of the screw. This property is aptly called the flowability of the solids. If the extruder doesn't receive a constant amount of material entering to match what is leaving, the output will be variable, which can cause inconsistent filament diameter or even cause the filament to break at the die when the spooler pulls on it. Some shapes are more likely to plug in the hopper or feed port than others. We didn't talk about it earlier because the regrind from the 3D printed parts had enough flowability as to not be a problem. However, thin film scraps or flakes that are produced from recycling most plastic containers, such as water bottles, have terrible flowability. We can visualize this with a simple angle of repose experiment, which is accomplished by placing material in a funnel that is sitting on a flat surface and lifting it up to see how the material behaves. For granules with high flowability, the material will spread out as soon as the funnel is lifted. For low flowability, the material will not diverge much from the shape of the funnel. The angle of repose is the maximum angle measured upwards from the table at which the pile will remain stable, without any of the material sliding downwards. Free-flowing materials have an angle of repose less than 45 degrees, with properly flowing materials having a larger than 45-degree angle. Here you can see that new PET pellets are highly flowable, with them spreading out to almost a single pellet layer, creating a very low angle of repose. The PET regrind, on the other hand, couldn't have performed any worse. It moved very little once the funnel was lifted. It has almost a 90-degree angle of repose. And for your reference, here is a 3D printed regrind from the first part of this video. The angle of repose here is between the new pellets and flake. Such a simple measurement can indicate if recycled material is going to be difficult to handle. In the case of this water bottle flake, Andy or I will have to sit next to the extruder and cram the plastic down the feed port. Industrial machines will use crammers, agitators, and/or separate feeding screws to automatically convince poorly flowing materials to make their way down to the screw. While tedious, this poor flowability is a problem that I can solve with manual labor. However, PET flake also suffers from poor solids conveyance once it's inside of the flights of the screw. To explain this issue, take a look at this threaded rod with a nut on it. The threaded rod is the screw in the extruder, and the nut is representative of the flake that needs to be conveyed forward. If I hold on to the nut and spin the screw, the nut advances axially. But if I let go, then the nut spins with the screw and we don't achieve any forward conveyance. In this simplified example, my fingers, or lack thereof, represent the frictional forces between the plastic material and the barrel's inner surface as the screw rotates. In a single screw extruder, we want high friction in the feed section of the screw for conveying the solid plastic material forward along the barrel of the extruder. In the case of low frictional forces, the material will fail to advance and spin with the screw. The heat from the barrel will melt the spinning regrind in the feed section, plugging the extruder. Not good. The low density and thin, smooth shape of the PET flake results in low frictional forces. Unfortunately, there's not much that can be done on my end to solve this problem. To properly handle flake in the recycling industry, the extruders are designed with special grooved barrels to increase this barrel to material friction and may have a conical shape to compress and increase the bulk density of the flake. In my first filament production video, I discussed how the screw needs to be selected to match the plastic. But as I hope you can see now, other extruder components also need to be adapted for the shape of the material. I can make the flake a little easier to process if I introduce some pelleted material to increase the bulk density and the frictional forces. These pellets are 100% recycled material that I created while testing different extrusion parameters. Obviously, reintroducing them again adds an additional heat cycle, which will result in some degradation, but there's not much that I can do besides this. One thing I learned during testing was that too high of screw speeds can cause premature melting, which increases the potential for plugging in the feed section. I'm going to take the extrusion process nice and slow and expect a highly irregular output. Even if I can't spool it, I will collect the strands and pelletize them. Once I get it to a pellet, many of those aforementioned problems will be resolved during the second round of extrusion. Take a look at this montage of processing the bottle flake to a 3mm filament, pelletizing it, and then re-extruding it to a 100% recycled spool of filament. So after about 4 hours of on and off work, I have a 1 kilogram spool of PET from water bottle plastic. I've been eagerly waiting to print something with it. Let's load it up on one of the borons. While the 3D printed part turned out nicely, you might be shaking your head saying that was a lot of work for a 1 kilogram spool. And yes, it was. But I went through this process to highlight that plastic extrusion is highly dependent not only on the plastic type, but also the shape of the regrind. Now that those water bottles have been turned into filament, it'll be much easier to recycle them the next time around. But to efficiently recycle common household plastics, which are often thin containers, specialized industrial equipment that costs orders of magnitude more is needed. It's a bit loud, but I want to end this video with what the recycling lineup does best, and that's turning unwanted 3D prints back into filament. Of course, we've got the reclaimer grinding the parts down, we've got the extruder extruding a 3mm filament, and we have the pelletizer and spooler working together to create a 3mm pellet, which will ultimately be re-extruded as a 3D printer filament. Hope you enjoyed the video, and with that, I'll catch you in the next one.